928, we're going to check conditions for carrying out a test with a population proportion. So the three conditions that we're going to test for a population proportion are the same that we would for a confidence interval. So the first one is you must have randomness in your sample. The second one, you must have an approximately normal distribution. So you take your probability of successes and your failures. Take your sample size. In this case, they're going to call it times p naught, not p hat. Must be greater than or equal to 10. For failures, you're going to take your sample size, 1 minus, again, p naught, which is going to be your proportion null hypothesis, has to be greater than or equal to 10. And the last one, we have to check for independence, ensuring that the population is greater than or equal to 10 times the sample size. So let's go ahead and go back to the basketball player claim problem. Remember, in this case, our hypothesis for the null case was the true population proportion is equal to 80%. So let's first check for the randomness part on here. It was pretty straightforward in that we looked at a set of 50 shots as an SRS, so a simple random sample. To check for normalcy, let's just use the appropriate rules up here. So for the normalcy test, first thing that we're going to test is that n times p naught, and p naught was 80% in this case, is greater than or equal to 10. Then for the probability of failure would now be 20% times this, which is greater than or equal to 10, so it actually just meets that requirement. Now, the one thing to be cautious of, remember in the confidence interval, the test for normalcy is n times p hat, which is our sample proportion. In this one, when we do a significance test, it actually assumes that H sub O, or our null hypothesis, is actually correct. So we use our P naught or our P sub O for that case. So be really careful. This is probably the one thing, if you make a mistake, it would be confusing again, the conditions for the confidence interval versus that of the test for the proportion. And then the third condition is going to be looking at our independence. Now in this case, this is more unique. We are not sampling without replacement. It's one shot, then the next shot, then the next shot. Replacement is not an issue. So technically, we do not have to talk about independence at all in this case. And a lot of the free responses in this case don't even mention it. However, we could just state, we could assume no independence is met because we're not sampling without replacement. Also, I encourage you to go to that handout of all of the various tests and confidence interval rules that I've given you. You will find the one for the one sample Z interval right here, where it shows the statistic, the conditions to be met, and where to find the test on the calculator. Now let's talk about the test statistic that we use for this one. You will find this definition here on the formula sheet. It's a very broad definition because from chapters 9 through 12 now, we're going to be talking about the test statistic, and it changes based on the type of test we're doing. What the test statistic is it measures how far the sample statistic diverges from what we would expect if the null hypothesis were true. And it's going to be in standardized units. So what it's going to look like is something like a z-score, where we take our statistics minus, it used to be the mean over the standard deviation, but for a test, we're going to take the statistic still, so it's going to be basically our p hat in this case, minus, notice the parameter, what I stated here, the parameter is the null hypothesis. So this will actually become the null hypothesis here, is what they mean. And then we're going to do the standard deviation of the statistic, which comes exactly from the statistic. The thing to be cautious of then is really about this particular parameter here. That's the one when we're actually using the H naught information. When we talk statistic, that is from the data, and so is this statistic from the data. So based on just what I said, if we go back to the free throw example, its test statistic, the standard formula is this. We are doing proportion, so it's a z-test, but we're going to take the statistics, which is p hat, minus, again, the hypothesis, which is p naught, over the standard deviation of the p naughts you have to use. Again, the hypothesis test, as it differs from the confidence interval for proportions, hypothesis test uses p naught, whereas the confidence interval is using p hat, so don't make that confusion. If you were asked to compute the statistic, which you could possibly see in a multiple choice test, for, again, our free throw, remember the free throw, the null hypothesis was 80%. We're going to calculate the standard error for that null hypothesis using the 80% and our sample size of 50. Now the actual sample, when we did it for the free throw individual, he made 64% of his shots. So based on this, the test statistic comes about as a negative 2.83. Okay, now they want us to actually find and interpret the p-value. So for this test, remember the hypothesis stated that h sub o p is equal to 0.8, but the alternative thought it was actually less than 0.8. So they do want us to find the p-value for this. So if you looked at a quick sketch of it, by the way, the z statistic is coming in at a negative 2.83, which is down here. The p-value we need to find in the less than direction, so the p-value is to the left of that. We did assume and we checked the conditions that it's approximately normal. Therefore, what we can do to find the p-value is do a normal CDF on this. Notice we're going to go from our lower bound to our upper bound. And it's been standardized. This is standardized data, so we use the mean of 0 and a standard deviation of 1. Based on that, the p-value, or the probability, it's incredibly small right there. This is actually about 0.2% of chance of happening. So let's actually define and interpret that in context. Therefore, the p-value for this case says, if it is true that the player makes 80% of the free throws in the long run, then there is only about a 0.0023 chance he makes 32 of his 50 shots, which is where we got the 64% from. Now, as the confidence intervals had their state, plan, do, and conclude process, so does the significance test. Talk about what you should address in each of the 4 components. In the state component, what you want to do at this point in time is actually state your hypothesis, identify the significance level you're choosing, what's your alpha, and define your parameter. So when you state your hypothesis, remember, do your h sub o and your h sub a for p, define what p stands for, and then again choose maybe 5%, 10%, or whatever being defined. The plan is going to be the same as we did for the confidence intervals. We're going to choose the inference method, so you're going to state what you're doing. Is it a one sample z test or a one sample t test? And then you're going to check your 3 conditions of random, independence, and normalcy. The do portion, I am going to show you how to do it by hand, but I do recommend using the calculator for your best and most efficient method. What you do want to show is your computation of the test statistic. If you use the calculator, it will show that for you, and you can just write the final answer down. To get away with not showing the formula, again, you must state the inference method. Then you're going to want to show the p-value. Either write it down from the calculator or show your calculation. Now the conclusion here, you are going to do, for your test, you're going to interpret it in context of the problem. And we'll talk more formally about, again, the conclusion is when you compare your p-value to alpha, you reject or fail to reject, and you make a conclusion of what you accept. So the 4-step process for this can be quite intense, but for the rest of the chapter, all we're going to be doing are confidence intervals and hypothesis tests, so you're going to get very used to this process. Now, section 9.2 is all about a one sample z-test for proportion. So that's actually the name of the inference test we were going to do. Remember again, all 3 conditions must be met, and your test hypothesis must be stated in terms of what you think your p-naught is. Be really cautious about your test statistic in this one. Again, I can absolutely see the AP board asking you to choose the right formula for this one. They're probably going to have p-hats in here versus p-naughts. Just know your difference. Finding the p-value we touched on briefly. If your alternative hypothesis is stating that the true proportion is greater than a value, that means when you find your test statistic, you go to the right because you want the greater than value. If your alternative hypothesis says the p-value is less than a number, you're going to find, again, your test statistic, which will probably end up being negative. It may not be, though, and you want the less than value. If you end up having a 2-sided test, remember what that means. It means your proportion is not equal to something, so it could be either greater than the z value or less than the z value for that particular test. Now, what happens when you've done your test and the actual analysis that you've done here, the data doesn't support h sub a. So if this was our particular hypothesis, what would that mean if the data does not support it? All it means is that the sample does not give evidence to support H sub A. So what you would do is you would just stop the test and you would fail to reject H sub O. So that means if you're checking the conditions and something breaks along the way, so you can't move forward, you just go ahead, stop your test, and you would say, because I don't have enough evidence to support H sub A, I fail to reject H sub O. And you cannot conclude H sub A takes place. I will tell you on actual free response questions on the real exam, I have never seen them ask you to take a test, and it was never possible to do. That doesn't mean it wouldn't happen, but I've never seen it to date. Let's walk through one example from start to finish on state, plan, do, and conclude. Here we have shows like American Idol. Contestants wonder if it's advantageous to perform last. To investigate this, a random sample of 600 American Idol fans is selected and are shown the audio tapes of 12 never-seen-before contestants. For each fan, the order of the 12 videos is randomly determined. Thus, if the order of performance doesn't matter, we would expect approximately 1/12 of the fans to prefer the last contestant they view. In this study, 59 of 600 preferred the last contestant they viewed. Does this give convincing evidence that there's an advantage to going last? So the first thing we want to do is actually state our hypothesis, choose our significance level, and define P. So in this case, we want the test the following hypothesis. I'm going to choose a 5% significance. That is the standard one. I recommend you always choose it. Now in this case, H sub O, the true proportion we believe is 1/12. However, we believe if it's more advantageous, it would be a greater than scenario. Now, the only other thing you'd want to do somewhere is define what P is. So it's going to be, again, the proportion of fans that favor the last contestant, and that would be sufficient. You do not necessarily, I will tell you, have to state this right here. If you just had this information at a minimum showing this, and definition of P, you'd be just fine. Okay, let's do the plan portion. So let's state the test we're going to do. You always want to decide if it's one sample or two, is it Z or T, and is it for proportions or means? That's really all you have to say. Well, this is a one sample. It is for proportions, therefore it's a Z test. So I'm going to say it's a one sample Z test for P, and I've gotten credit for picking the right test or confidence interval. Okay, for randomness now, let's just talk about that. A random sample of American Idol fans was selected, and that order in which the video was viewed was randomized for each, so we're fine. Check the normal condition. 10 times P naught in this case, where P naught is 1/12. So 50 is greater than or equal to 10. Let's check if the failure rate of that one, it would be 550 is greater than or equal to 10, so it's approximately normal. The independence component, it is reasonable to assume that there are more than, remember 10 times our sample size, more than 6,000 American Idol fans, so our conditions have been met. Now for the do portion, I'm just going to show you a few key statistics that I would list, and then I will talk about the calculator keystrokes. So for the do portion, the P hat in this case, 59 out of 600, so 0.098 is P hat. So if they asked us to show the test statistic, again, if you actually tell them the test you're doing and just for the calculator output, you would be fine. But it's good to see this test statistic written out. It's going to be P hat minus P naught over the square root of P naught times 1 minus P naught over N. So our test statistic is 1.33. Now, if we think about what we think the diagram would look like for this, here's a good picture of it. Our test statistic comes in right here at 1.33. Remember our hypothesis, we thought it was larger, so the p-value calculation is actually going to find this for us. In the calculator, it's actually very easy to find this. Remember, we're going to hit the stat button. When you hit the stat button, you're going to get these options, go over to the tests. In this case, we want the one proportion Z test. If you select this, it's going to actually ask you for what your P naught is. Our P naught in this case is the 1/12. You could type 1 over 12 and it'll just convert it to a decimal if you want. Then you want to give it the actual information about the P hat. So how many successes were there? There were 59 successes out of a sample size of 600. Choose which test you want. Was it a two-sided? Was it a less than or greater than? It was a greater than test. And then I can go ahead. It actually does give you the option, by the way, to draw. If you select draw, it will actually sketch this for you. But if you go into here and select that you want to do the calculation, it will kick this back as your calculation. Now, what I would write down, I personally, just to kind of cover myself, would write down all of these elements on my piece of paper for my actual free response. So let me show you where everything is. This prop that they have written right here, that is actually our P naught, which we used right there. Our Z is technically our Z score, or our test statistic that we computed. I'm next going to look at the P hat. The P hat was right here at 0.098. And then clearly our sample size we see, and we know that that was the 600. Now there's one thing we didn't talk about on this screen yet, and that's the letter P by itself. Well, what that is, if you don't recall, that is actually our p-value. So this is the p-value, or it's our probability. So in this case, I actually do not have to compute it. Now, let's say I was doing this by hand and I had my test statistic. I know I'm looking for the area above, so all I'd have to do with this test statistic is I could easily compute the p-value just doing normal CDF. I would 1.33, and they chose all the way up to 100. You could put 999. Now, they did not technically put the 0 and the 1 here because that's the standard, but you could. Based on that, your p-value is 0.0918. So it's a 9.18%. So based on that, let's wrap it up with the conclusion. Remember, on hypothesis testing, you must state 3 things for your conclusion. First thing you must state, in this case, P is greater than alpha. So I need to actually show the calculation right here. Because P is greater than alpha, we failed to reject the null hypothesis. And then we're going to make a conclusion. So there is not convincing evidence to conclude that there is an advantage to performing last on American Idol. And that's how you would do a one sample Z test for proportions from start to finish. If you would like to see another one, I'm just going to walk through this one very quickly. So feel free to jot it down if you'd like. The scenario is this. According to the National Campaign to Prevent Teen and Unplanned Pregnancy, 20% of teens ages 13 to 19 say they have electronically sent or posted sexually suggestive images of themselves. The counselor at a large high school worries that the actual figure might be higher than that. It's helping us with the hypothesis. To find out, she gives an anonymous survey to a random sample of 250 students at her school of 2,800. 63 admit to sending sexual images. Carry out a significance test. They are telling us to do 5%. What conclusion can you draw? Well, we know we can talk about the proportion, the significance, and state the hypothesis. We're going to do, in this case, a higher than for the hypothesis. So here's what I would say for the state. We want to perform a test at a 5% significance level. Our hypothesis is P is equal to 20%, but the counselor thinks it's greater than 20, where P is the actual proportion of teens at the school who would say they have electronically sent or posted sexual images of themselves. Okay, for the plan, let's check the conditions. We are going to do a one sample Z test for the population proportion. Randomness is covered in here. For normalcy, n times p naught and n times 1 minus p naught are both greater than or equal to 10. Independence, there were 250 in the sample, which means I have to have at least 2,500 in my population, which I do, so we're good in meeting that condition. We can now move on to the do portion and compute the statistic. The sample proportion, or p hat in this case, was 63 out of 250. That's where p hat came from. I'm going to put this information in the calculator. For p hat, it's going to ask me for the 63 and the 250, and for p naught, I'm going to put 20, and I'm going to say it's a greater than test. It will kick back this test statistic, and I want to go a p-value greater than that. So the p-value that's going to come back on the calculator is 0.0197. We can make a conclusion. We can say since our p-value is less than 0.05, we reject the null hypothesis, and it appears that the counselor's concerns are valid that there are more than 20% of the teens at our school would say they have sent or posted sexually suggested images of themselves.